Hi, everyone. Welcome to the DeSci Labs December 5th community call. Excited to be talking about persistent identifiers today. So this is definitely a big topic that we have touched on in the past, but this is a more explicit call on the subject. So it's going to be fantastic. As always, we're going to go ahead and get started with some quick updates from everything around DeSci Labs. So Carla, do you want to give us a quick update on node stewards?
Yeah, for sure. So last week was, I think, the 1 month anniversary of the program. So that was really cool. In this 1 month, I think we built a really cool community, and everybody had the chance to build out some skills that you need for the node steward role. And we were able to identify a couple nodes already that would make or a couple of pieces of research that will make some really cool nodes. And that's the goal for December. So we want to build a backlog of at least 10 pieces of research that would make cool nodes that show off the power of the technology that we're building. And if you want to be part of that mission, we have an onboarding call tomorrow at noon ET. So feel free to come join. It's definitely not too late to join the program. This is a rolling basis. So yeah, come join, be part of the community, and let's find some cool research. Oh, and another update from the foundation. We have a Future of Science seminar with David Aronchik from Protocol Labs. It's happening next Monday. It's always 1 hour before this community call. So yeah, go sign up. We tweeted about it. I also dropped a link in the announcements channel here on Discord, and we'd love to see you there.
And Carla, what's the exact subject of that Future of Science seminar?
Yeah, so David will be talking about compute over data, or the future of compute, what that could look like, and what it could mean for science. So that one should be very interesting. And the cool part is that most of the ideas are building on the previous seminar that we had on fair data, because fair data is definitely something that helps compute over data structures. So that's kind of cool.
Awesome. Well, it sounds like a great seminar. And right after the seminar, we will be having a community call that is focused on more discussion and free-form conversation around compute over data. So feel free to go listen to David, sign up through the Eventbrite and the announcements channel, and then come to the community call after to debrief with other community members. Sounds like a good time. Thank you, Carla. Does anyone else have announcements before we get started today? I'm going to take silence as a no. Chris, do you want to go ahead and take it away with persistent identifiers?
Sure. Great to be here to talk about this topic that is dear to me. And I would add also that it is quite an obscure topic. I mean, PIDs, what does that mean? Well, it means persistent identifier. Well, what is a PID? So for longest time, we have a lot of PIDs for a lot of things. For example, a license plate number is a PID. Your social security number is a PID. There's a need to essentially have what you can think of as a master key, or essentially a key that has some guarantee of uniqueness, that it is uniquely describing a specific object. And that's very, very important in order to be able to maintain a good, quality databases without any collisions within that database. More broadly speaking, PID are essential because they allow us to have better interoperability across different services. So if you have, let's say you have a social security number, it will allow you to link all sorts of different government services together in a way that allows interoperability between all of these services. So it's quite fundamental as a way to allow different types of silos, services, databases to interact and connect together. Now, very dear to our hearts here at DeSci Labs is the PIDs of the scientific record. So every publication, every research object, every entry in the scientific record nowadays is accompanied by a PID. And I will just preface this saying not all of them, but the vast majority of them. PIDs, the PID that is typically the one that is employed is called the DOI, Digital Object Identifier, DOI.org. A DOI essentially is a link that can be used, that will be resolved, and that should resolve to essentially the page of the publisher that contains that specific piece of published research. So DOIs are essential, and DOIs have a long story. So DOIs were Sorry, we have quite a few animals here in this room.
Why don't we go into the other room over here?
I'll feed them.
Yeah, I think it's better now. So essentially, DOIs, digital object identifiers, are a way are the PIDs of the scientific record. Now, these PIDs are essentially handled by DOI.org, which is a website and a service that was initially created by the American Association of Publishers. During the time where there was a digital revolution, so I think it was in the late 90s, early 2000s, the American Association of Publishers came together and they needed a way to track who owns what copyright, who's allowed to sell which type of content, and so on and so forth. And because they had this incentive alignment that allowed them to essentially decide who owned what piece of copyrighted content, it essentially became very, very widely used within the scientific publishing ecosystem. That is not the case for branches of science that have historically not depended that much on third-party trusted intermediaries or publishers, like computer science, for instance. So these PIDs are essential because they allow us to derive what's so-called PID maps, which allow to link things like researcher identities, funders, the specific research objects to which it's connected for, the specific manuscript that have been produced by these scientists. And you have now different services across different specialties that provide PIDs, persistent identifiers. You have things like ORCID, which is essentially a CV for academics that gives them a number, which is a unique identifier. You have services like ROAR, which is specialized for funders, to give funders a unique number that can be then added by researchers into their research. And the goal of this entire effort is so that we can have a very deep visibility into the process of creating new knowledge, knowing who has created that knowledge, who funded that knowledge, what is the status of that specific object. Has it been retracted? Has it been corrected? Has it been modified? Essentially, how many citations it has gathered and all of these things, right? So in order to allow interoperability across silos, in order to allow for federation of content, you need these persistent identifiers. So that's a bit of the context on PIDs, and I'm going to be just throwing a few useful links here for people who are interested into the chat. So DOI.org is the PID of choice for the scientific record today. Now, what does it rely on technologically? So DOI.org essentially works off the so-called handle system. The handle system is a very ancient system that I think was essentially devised in the 90s to provide these digital identifiers. So I'm linking a few of these in the chat. So we have ORCID, we have ROAR, we have DOI.org. These are some of the more widespread ones. I'd also link the Freya project, which is a project funded by the European Union that has looked at the use of PIDs in science, and you can learn all about the benefits of having PIDs. They also have a forum where they discuss these things in length. Okay, so this is the current state of the art. Now, there's a number of problems with this infrastructure. One of them is that essentially PIDs suffer from content drift. That means the underlying content can change on a website, let's say a publisher website or a repository of some form, but the PID remains constant. And that's an issue. That's called content drift, or you could think of that as reference rot, which is also a technical term for content drift. There's another big issue surrounding PIDs is everything that has to do with versionability. So now if I have my manuscript on a preprint platform, I get one PID, I get one DOI for it. And then I get my manuscript published by, let's say, a publisher, and it's published in a journal. Now I get a new DOI. And you start having a proliferation of these PIDs around a single research object, essentially, which leads to artifact fragmentation. So what does it look like today when I, as a scientist, want to register and get my PIDs? Well, I have to get one from my publisher or my preprint platform. I get a DOI. Then I need to do a code release on GitHub and get a DOI from Zenodo. And now I get a second DOI, which is related to my code. And then I have to go on yet another platform like Dryad and go through this entire process of uploading my data to get yet another PID, and so on and so forth. So I end up with this vast collection of PIDs, DOIs, and I now have to rely on services to link all of these PIDs together so that these artifacts are not lost. The services that typically do this today are Crossref and DataCite, but they do this via the intervention of publishers. So publishers are typically have the responsibility to aggregate all of these PIDs on their webpage. Now, this is not done in a way that is very interoperable, and that's one of the big issues here. So these PIDs, as they're currently conceived, tend to lead to a lot of artifact fragmentation. On top of that, the user experience is pretty dismal because you need to go on all of these different services across all corners of the web. And by the end of the day, or the end of the multiple days it might take you to do this, you end up with a collection of DOI you then send to your publisher, and the publisher has the responsibility to keep these objects consistent and congruent into one singular collection of PIDs linking to that specific research you've published. Another side effect of this, so we talked about artifact fragmentation. Another side effect of this, which is very relevant now for scientists in their daily life, is the so-called problem of citation fragmentation. So what does that mean? Ideally, when you publish a piece of work as a scientist, well, you want that piece of work to be the object that is accruing credit in your social context, in your community, within the scientific community. Now, if you have a separate PID for your data or separate PID for your code, you don't necessarily want these other objects to start accruing credit. You'd rather have that central object, that typically a manuscript you've published, to be the object accruing credit. And then if you have a manuscript on a preprint that starts accruing citations separately from your main published manuscript, that's a problem known as, that's a form of citation fragmentation. And I think there was even a study on this looking at PLOS biological preprints showing that there's about a 10% citation loss for papers published in PLOS due to citation fragmentation happening at the stage of the preprint publication. So what does that mean? That means you create adverse incentives. I don't want to have citations fragmenting of my research. I don't want to spend days and days or many, many hours going through all of these different services to get my PIDs. And after doing all of this effort, I just increase the odds of having citation fragmentation. And on top of that, there's also the problem of content drift. So there's no protection against the fact that these underlying objects might change over time. And they might change for malicious reason, because let's say there's some attack on the information infrastructure, which is for example, there's this case of Elsevier changing the time to publication date when essentially it's really looking bad for them. But more important than malicious effects, there's just the fact that as a scientist, I might version my work. And when I'm citing someone else's work, I want to actually cite the version that I actually read that supports my claim. So these PID systems are not good. They're not made to handle any form of versioning whatsoever, right? So to sum up, PIDs are essential because they allow us to form PID graphs, to understand provenance, to understand how things were formed, to allow for systems to accrue credits on these manuscripts, these published papers, these research objects. They're fundamental because they allow for greater interoperability. The current infrastructure was born out of a need to transition to the digital age. in the early 2000s by the American Association of Publishers, who had an incentive alignment at that point to adopt the DOI system in order to keep track of copyright ownership. That system has quickly needed to adapt to greater needs in the research community and in the information management economy, specifically when it came to metadata. And so you had services like DataCite and Crossref that appeared and started adding metadata linked to these PIDs so that we could have greater and greater interoperability. So you could think of that as an emergent system that has created all sorts of, you could say patchwork solutions to address the problems of the time as they came in. And now you have other PID providers like ORCID, like ROAR, who are working on creating PIDs for all sorts of other parts of the scientific production process in order to reach this ideal of having PID graphs. In terms of the limitations of that system, artifact fragmentation, we lose pieces and parts of the scientific record. We have bad UX, bad user experience for scientists who need to spend time on countless different services in order to gather all these PIDs. The fact that we rely on the publisher to collate and combine these PIDs into research objects, and the fact that they have no systems in place and no syntax in place and no schema in place to allow for versionability, because that's not what they were designed to do. So all of these things together make this entire infrastructure to be quite clunky. And again, I'll direct you to read the report on the Freya project and the PID graphs, and there's other parts discussing problems with persistent identifiers in the current infrastructure. And finally, another point I haven't yet mentioned is the problem of inconsistent resolution. So every PID to be useful needs to be a link. If it's not a link, it's not useful for users. Users want to be able to click a link. The problem with that is when you click the link, you don't know where you're going to end. You might end on the page of the publisher, you might have a paywall, you might end directly on a PDF, you might end in all sorts of different places where you don't necessarily want to be. People, when they click a DOI, they want to resolve on the object of that DOI, which typically is the manuscript, and that's what users want. And there's a running joke, which is, what's the best way to resolve a DOI? Well, it's actually to copy paste it in Sci-Hub. That's the best way to resolve a DOI. So all of these things together, this is one of the topics we've spent a lot of time understanding what are the potential of the technologies that we're building in order to improve the current PID system. So how does it work in DeSci? So in DeSci, we're essentially creating a PID for linked data objects. So what does that mean? That means you can have your manuscript, you can have your code, you can have data, you might have a video, external links, all sorts of resources that are connecting to that research object. A single PID minted in DeSci allows you to reference an arbitrary number of components that is connected to your research object. That means you can refer to the data, you can refer to the code, you can refer to the manuscript, you can refer to versions of each of these components. So you have versionability built in, you have the ability to address arbitrary components within that research object with a single PID. And that's a pretty powerful thing. That means you can now type things like, hey, PID / my data / my measurements.csv. And you can resolve this over HTTP or over IPFS, and you can get to that specific file or arbitrary byte stream that's being encoded in that object. And you can do this with a single PID. Now, the power of this is that we can create PIDs that now act as file paths. Everyone is familiar with file paths. Everyone's familiar with tools like Dropbox or Google Drive. And if you can think about that, you can think about these tools, these commonly tools that everyone uses nowadays. And you could say, well, now if I have a single PID that I control that allows me to refer to every connected object within that folder, that gives me not only a tremendous benefit in terms of user experience, because I can get all my PIDs with a single publishing platform, But I also have the ability to version them, and I have the ability to granularly address them. So that means now that we not only can dramatically improve this problem of artifact fragmentation, but we can also allow for very granular citation. So I can cite code, I can cite data, I can cite any linked resources to a DeSci PID without citation fragmentation. The credit of a citation accrues to the research object itself, to the root of that research object. And that means we no longer have this incentive misalignment issue that is currently a problem with the scientific record. Another part that's very powerful about these DeSci PIDs is that they do not rely on a trusted intermediary because we use the content addressed web. So it's all on IPFS. That means every file that's added in that object, we essentially have a guarantee that those files have not been changed by the platform. And so what does that now allow us to do? Well, that allows us to really, not only have greater trust in these systems, but also have a much greater interoperability across different platforms or applications that might surface these DeSci research objects to interact with these PIDs. And finally, a really interesting point that comes out of all of this is now, if we have PIDs that allow us to address objects contained in a research object at an arbitrary level of granularity, we start being able to do really interesting things. For example, we could say, hey, you can have your Python IDE, and you could say, hey, import DeSci fetch, and import, PID / my code / my version 1 / myanalysis.py. And you could start importing code file and data files through HTTP directly into your IDE as a researcher. And now that starts becoming very interesting because I further reduce the cost, the user friction for reusing components and artifacts that others have published. Think about it this way. What if we could LS every paper ever published, right? What if we could just see what's in the file directory? What if we could import data, code, and all sorts of components very, very easily in one's working environment? So that's what we've had a demo of this. I'll link it later on YouTube, where we demonstrate this so-called example of citation as function call, which is this idea that Balaji Srivastava has been pushing for a while. It's essentially this ability to create truly composable science, where you can import functions, where you can import scripts, where you can import data directly in your IDE from other published work, and all of this data is essentially on the content addressed web. It's verifiable data. It uses these cryptographic hash functions to essentially create a common namespace for all of it. Now, there's, of course, a limitation to IPFS. So IPFS is interplanetary file system. It's a content address storage network. It's a fantastic backend in terms of creating reliable, tamper-proof information. But it has a limitation in that it doesn't make for friendly links, because nobody really wants to click on a link that looks like a hash, an SHA-256 hash. These links get very long. They're not human readable. They have the properties of being decentralized and secure. And we need essentially some sort of URL shortener, right? You could think of TinyURL. I'm sure a lot of you are here familiar with TinyURL. You take these arbitrary long URLs on the net and you want to share them with your friends, but you're looking at the size of them. You're like, well, no way, this is like a 2-page URL. I'll go on TinyURL and get a shortened version. And now all of a sudden it's very usable by humans. Well, in DeSci, when you create a research object, you not only have these very, very long but cryptographically secure links that allow you to refer to your entire research object, which have these IPFS hashes embedded into them, but you have at the same time a registry which performs a URL shortening function which then provides you with really short and sexy links that you can use as a human much more easily, right? So these are really short links that are similar in size to DOIs and that have this greater ease of use. Now, in terms of the underlying theory behind that, there's a very famous problem in computer science that's called Zuko's triangle. So it's also one of the best names in terms of problems I know in computer science. So Zuko's triangle is essentially one of these optimization problems where it's not possible, at least the conjecture goes that it's not possible to have a namespace or naming system that's decentralized, secure, and human readable. And famously, Aaron Schwartz, of all people, solved Zuko's triangle by proposing DLT as a way of solving for Zuko's triangle for having the third property of human readability in the namespace. And so that's essentially what we're doing. So we're building out on these foundations to create not necessarily human readable names, but short URLs, right? So we create short URLs similar to tinyURL that have these properties of being secure and decentralized and short and usable for humans. And the superpower that they contain is that they're versionable and that they allow to address at arbitrary levels of granularity components of research objects, which is something which we believe could help dramatically reduce artifact fragmentation, citation fragmentation, which is a big problem in terms of incentives, and promote more composable and interoperable research, because all of a sudden you can import data, you can import code, you can import all sorts of things directly in your IDE from PID. So to sum up, imagine if you could have a DOI and you could just pass it in your IDE and slash, hey, DOI from this paper I really liked, from this that had this really interesting theory and data set, /data /measurement.csv, and boom, you have it in Python, your IDE, or somewhere else in R. I don't know. So that level of interoperability at a very fine level of granularity is what we want to do. And the next, finally, like the really interesting part about these PID systems is that if you commit a DeSci node that is essentially referencing PIDs from other DeSci nodes, well, we can automatically credit them, right? We can go through these files and we can create automatic credit accrual mechanisms to recognize that these artifacts have been reused. And one of the biggest problems facing science right now is, and of course it's linked to reproducibility and replicability, but it's this issue of like, hey, how do we accelerate the reuse of scientific artifacts? How do we prevent them from being lost? How do we make them more findable and interoperable and reusable, which is very much, the essence of these FAIR principles. And so what we really hope to achieve is using this DLT/IPFS-based PID systems that we're developing in DeSci Labs, we can really help solving and addressing a lot of these core issues in the scientific record. Okay, so I've been going on for a while now. I'm really happy to open the conversation, take some questions, and dive deep.
I think PIDs might be one of my favorite subjects that we talk about. It is fascinating the way that this whole system works. So I do have a quick question for you, and it's something that you've touched on in past calls, but I would love to hear a little more elaboration on that subject. The existing DOI system is kind of the foundation of a lot of academia, and there are other things that are built on top of it. For example, Google Scholar. So one question that I have is around the way that this new PID system integrates to what's already there and how it can function as an on-ramp as well as a better system.
Yeah, so one detail about that is that Google Scholar does not use DOI to accrue citations. And the reason for that is that computer science, cryptologies, and a few other branches don't use DOIs at all. So, and this has to do with the historic relationship between publishers and professional societies. And yet these CS papers do accrue citations. So that's not like, for Google Scholar, it's not fundamental. For things like Web of Science, DataCite, Crossref, Scopus, then it becomes more of a critical part. But Google Scholar is a bit different in that regard. So ideally, we'd have some sort of backward compatible system, right? That's something we might, we're thinking about. We're looking about how we can do that. Still work in progress. What we want to achieve here is really create like a very elegant, proof of concept and system to really demonstrate the value that this can bring, and then work towards getting to some degree of backward compatibility. I think it's also important to mention that minting a DOI costs $1 from a DOI registration agency. They have different pricing, plus membership fees in certain cases. The DOI system is essentially a giant lookup table, which requires a social contract between the publisher who's putting the work up to maintain the link, the correspondence between that link, that URI, to the DOI in that lookup table. Now, every time that correspondence breaks, because it breaks a bunch of time, you have crawlers on Crossref who go automatically checking for broken links, for 404s. And every time they detect these 404s or conflicts, they have to send out messages to the publishers to remind them to fix their databases. So the system essentially needs a constant monitoring and repair infrastructure to keep it going, because they break. Every time there's a database migration in the publisher, well, it's going to break a couple of DOIs and could break a lot of them. So it's a very, very brittle system that relies on the publisher to be a trustworthy entity to maintain that DOI. That's very fundamental, because if the publisher doesn't do this duty, then that DOI no longer works. And now you have you can have a really, really big problem, and it's in terms of like the actual scientist who published his work, who no longer, his PID doesn't function anymore. And this is completely different with what in the DeSci space. You don't have that issue of needing, let's say, a DeSci gateway to have a social contract that says, well, that DeSci gateway is going to maintain that lookup table, is going to maintain that URI. It's not needed at all, because it's content address. The content addressing is essentially, we're not asking where a file lives, we're asking what it is. And the link, or that, is essentially the identity of that file. So now we can remove that entire additional maintenance burden, which is rather giant, and why you have all of these maintenance fees, right? And the cost of minting these DOIs. You can remove that altogether.
Chris, can you maybe explain a little bit what is the relationship between content address storage that IPFS offers and the permanent IDs that we will generate for the DeSci nodes? So how are they linked, or are they just literally the same?
Yeah. So essentially, we have on the back end, we have content identifiers, and we take that content identifier. There's a data model structure called IPLD, Interplanetary Link Data Structure, and so every research object is an IPLD object, and we take the root hash of that object. So we take the entire object that's hashed. We take that root hash and we index it on a contract. And in addition to this indexing on a contract, we also we essentially take that contract and generate a shortened link to that object, right? Which becomes the human-friendly PID. So that's the relationship. So what does that mean? That means there's always a relationship between the long-form URI that's content addressed and the short-form URI, which is not content addressed. Does that make sense?
Sort of. I'm still trying to understand exactly how these two things are linked.
Well, we have Sina right here, so he's going to give you some more detailed information on that.
The master himself.
Yeah, so content addressing is you take your data and then you run a hashing function on top of it, and it lets you basically create a fingerprint of that underlying data. And the fingerprint is a lot smaller than the data itself. That's a property that this has. And in our case, that fingerprint, that CID is 32 bytes, and it makes it very efficient to index that on a blockchain. And so what we can do then is use the properties of the blockchain that allow us to maintain provenance about, oh, okay, when was this particular fingerprint published? And it gives us guarantees around this due to the incentives within these different chains. So, for example, like Ethereum, we can feel very secure in the fact that, hey, this fingerprint came in at this time from this particular user, right? And then if the user wants to make an update at a later point to update the version, we'll have a provenance trace of these fingerprints over time, right? The thing is, if we only use the fingerprint to reference the data, we would quickly get out of sync. So we link these fingerprints with a canonical ID, which is tracked on the smart contract. That's what we're actually writing every time a new version is published. We're updating the canonical ID to point to a new fingerprint or content hash. And
Wow.
because the content ID itself is cryptographically secure, it's very easy to go one way, very tough to go the other way. So this content hash is cryptographically secure, and it also has the property that it's very, very unlikely that there's collision. So it's very unlikely for two different pieces of data to produce the same content hash. So we take these cryptographically secure hashing functions, use them to generate this fingerprint. We can change so we support version changes over time. It's pretty much anchored to this canonical ID that's stored on chain using a consensus mechanism that is trusted to work correctly to make sure that no funny business is going on. There's no unscrupulous actors changing this content ID or the canonical ID over time, so we can trust that it's all secure. And through this system, we can be ensured that throughout the whole from the canonical ID all the way down to the the leaves of the IPLD DAG, we can be ensured that the data is the same as when it was first published. And so that's the property that we're looking for. So yeah, this property of does this help answer your question, or I don't know, maybe
Totally. And
Okay.
so I'm just thinking. So a part of the property of the hash function is that it basically takes a string of arbitrary length and converts it into a string of a fixed length, following a mathematical function that, depending on the input, returns a deterministic output. But it's a one-way operation, right? And there is a really, really minuscule chance that you end up with the same hash for two different objects, right?
Yeah. So if you were to have a collision between two a piece of data, two piece of content, and if they were to collide and have the same hash, the underlying data would be wildly different, right? So it wouldn't be a research object, in this specific IPLD format that we're talking about. It would be garbage probably. If somebody was to go and get a bunch of supercomputers and run them for, I don't know, like I don't know how long, maybe 100 billion years, I don't know, and try and come up with collisions. But it would be the collisions that would come out would be very clearly not the correct data format, right? So basically we can rest assured that this the underlying hashing algorithm is secure, and even if it isn't, all right, and so in the future breaks, because we use tools from IPFS, we're using multi-format hashes. The beginning space, I think it's like the first maybe 1 or 2 bytes is reserved to basically point to say, hey, we're using this particular hashing function. So in our case, we're using SHA-256. But in the future, if SHA-256 was to break, we could transition to using a different hashing system because we're using multi-formats.
I
Sorry,
got it.
multi-hashes, yeah.
Okay, cool. So that basically guarantees that the address is unique. So what are the requirements that need to be fulfilled for this address to also be permanent?
Yeah, so when you say address, are we referring to the canonical ID for a research object? Is that what we're referring
Yes.
to?
Also, I mean, my question is very practical, right? So I mean, permanent. So nothing in the universe is permanent, right? So everything will ultimately collapse and like
Or expand.
its existing form in some way or another. So my question is, so what needs to break for the system to break? So what needs to break for the PIDs not to work anymore, not to resolve?
Sure. I can answer this. So there's a couple different points where this can break. So basically, one thing that can break is in terms of resolution, if the CID that we are attempting to resolve is not available, for resolution. That could be one way. So we wouldn't have access to the underlying data in that case, right? So we would have a CID, but then we wouldn't necessarily know, like if basically there was no node on the Filecoin network that was serving the CID, or no node on IPFS that was serving the CID, then we would not be able to resolve it, right? So that could be, we run out of copies of the data. So that's one thing that can fail, right? And then
there needs to be a guarantee in place, first of all, for the IPFS network to run, and the particular content that you've addressed needs to be stored somewhere on IPFS.
Yeah, it does need to be stored somewhere, yes.
Right.
And so, for us, we're doing a number of things on our end to create a story that to create a plan to allow for that to be the case in the long term, right? So for us, I mean, I think one of the things that we're committing to as DeSci Labs is to always host this at least the metadata, right? Indefinitely, and then there could be certainly cases where potentially it's like no longer cost effective for like a node to store like a large data set, for example. That could certainly happen, and in that case, that data set would then be offline. However, with our commitment to store the metadata, we will always have the metadata available to show, like if anybody was looking to resolve that information, they would at least know what it was pointing to and have some information describing that data. And that can also happen not only just due to a failure of like a node is no longer incentivized to store the data. It could happen due to like a node is like legally compelled to remove the data from its servers.
Yeah.
Right, so that can also happen. However, still we would still be committed to storing the metadata, and so we would still have a reference to what that data was in the first place. But what's really cool also about using the CID system is we don't have to put all our eggs in one basket. Those CIDs are like a portable way of describing the underlying data and giving it like a fingerprint that can be referenced in many different systems. So, we could, I could certainly see community-based projects coming out where, you're using that same CID and you're saying, hey, I really think that all these research objects deserve to be stored in the long term for the benefit of humanity. And it becomes very straightforward to mirror all this content onto several other different networks and have a lot of different resolvers for them. So it makes it very portable and easy to catalog all the data. So, just because we're using IPFS or Filecoin, is not necessarily a guarantee. I mean, at the end of the day, these systems, need to have the electricity running. There needs to be network turned on. All these things have to be true. However, by using the CID, the content address model, we make cataloging and organizing this information and making this information portable, like really easy out of the box. It's all set. It's all set for folks and teams to mirror all this content. It also gives us guarantees around it allows us to be confident that the underlying data was not tampered with, because it's very easy to verify that the underlying data matches that fingerprint that was initially recorded on chain.
Yeah, exactly. Because you can just regenerate basically the hash, right? So once you
Correct.
have the content,
So it's very easy to verify, right? So even if you have many different, if you have a decentralized, many different groups that have, different interests, and different desires, regardless of the different groups that are storing the information, regardless of their angle, right? If they're not going to be able to fake this hash. They're not going to be able to basically tamper with the underlying data because we're using this model.
Yeah,
so
exactly.
we can go through that.
Super cool. And the resolver, you mentioned the resolver a couple of times. So I excuse my ignorance, but I don't really understand what a resolver is. So how does that thing work? Is that a potential weak point of the system? Or no?
Yeah. So in our case, there's a couple places where resolution happens. So one was one I just mentioned. So it's like CID resolution. So currently CID resolution occurs on the IPFS network. So that's basically you give it a CID, and then a node in the IPFS network asks itself, hey, do I have the CID? It's like, oh yeah, I do. And then here's the content. I've resolved it for you, right? It serves the content. So that's one part. The other part is, resolving the canonical ID. So that would be like asking the Ethereum network, hey, what is this ID for this contract? What is give me the CID for that, right? And so that's another form of resolution. And then there's, I guess, like a third form of resolution that we're proposing, which is the DPID resolution scheme. And so this kind of puts it all together in the context for science and scientific publishing. So it basically says, okay, you give me a short readable URL that has been registered on the DPID contract, and it may have actually a bunch of stuff after the canonical ID. And when I say bunch of stuff, it may be actually pointing to a part of a data structure that's been stored, like an IPLD data structure. And so what it'll do, it'll make that call to the Ethereum network on your behalf. It'll then make an additional call to the IPFS network, and then it will actually determine which component you are referencing, like in the suffix, and then basically it'll figure out what to do with that suffix in a way that meets the needs of what we've defined as being this resolution scheme. So it could be like, hey, we want you to actually return. So if you're trying to get or cite or resolve like a data component within a DeSci node, you could reference that explicitly in a URL, and so that would and it could be a DPID URL. And so we would, the DPID service would then resolve the canonical ID, resolve the IPFS CID, and then potentially do another IPFS call to resolve the data component that's underlying and being referenced in the URL. So that DPID resolution scheme would be, an open source, permissionless way to resolve these identifiers. With fine grain citability, you can actually reference with fine grain precision elements stored within the metadata, right? And you can pull in different components and that sort of thing. So there's different things that you could refer to as resolution. So the main one I think we're focusing on is that DPID resolution, which kind of brings it all together and makes it useful for the scientific community.
And does
DPIDs are the bridge to make the content identifiers useful for humans and the scientific communities.
And so that DPID resolver is just an open source program that in principle anybody could run, or
Correct.
that just going to be automatically executed whenever somebody uses an ID to call up an object. Is that correct?
That's the idea. So it's like you can think of Ethereum, making a DApp or like a smart contract call a read operation on Ethereum. A read operation on Ethereum is always free, and it's available for anybody with an internet connection. And then also with the IPFS network, requesting information from the IPFS network is also a free operation. And the DPID system just puts those two together and adds some convenience rules to that to make it useful and usable. And that that is open and it cannot be censored. And so none of that is censorable according to the rules of these networks that we've described.
Cool. Thanks.
Great. So I'm really happy. I'd love to grab some questions. If anyone has some interesting things to mention or questions here, we'd love to be able to chime in.
Hi, I have a question about the versioning system. So there's canonical ID, and then there are subversions. So what is this underlying structure? That how does it look like on the back end?
Yeah, I can answer this.
Yeah, sure.
So yeah, the canonical ID right now it's effectively it's like you could think of it like a hash map. So there's a key and a value, right? And so the key would be the canonical ID, and then the value would be the content ID of the current version. And the way that we've implemented this on EVM compatible chains is that we update every time the CID is updated, an event is emitted on chain, and so then you can actually trace all the different versions of that particular canonical ID by inspecting the event log.
Yeah, so that means we have versionability, and you have a trace of provenance with all the prior versions as well that have been committed.
Right. So, but does it change something in terms of IPLD?
So the IPLD part is so actually technically a user could, because the system is permissionless, technically a user could add a value that is not IPLD compliant. It could also be garbage bytes. It could be a CID that doesn't resolve to anything. They could do that. However, it wouldn't really benefit them to do that, and so our system is designed to only index IPLD compliant data CIDs. And by using that system that would be available for anybody to use in open source, you would be able to reap all the benefits that we've described here, the provenance checking, version history, that sort of stuff.
But I mean, so suppose somebody just updates a version of their preprint, for example, and like happens on archive. So what's happening in this case?
Yeah, what would happen is that a CID would be calculated for the research object. So let's say like you had so on archive, you could think of it like a research object. Most of the time it's just a PDF, but let's say like there's like a JSON structure or something, right? So it's like PDF equals blah 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 PDF, and maybe link to your GitHub is like blah 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 github.com/whatever, and that's like a JSON file, right? That has those links, right? Let's say, and then we would calculate the CID for that JSON file effectively, and then store that CID on chain on the canonical ID. And then if somebody then makes an update, let's say changes the PDF to PDF version 2.pdf, there would be that JSON format. The CID would be completely different because the underlying content is changed. The user has permission to then update that canonical version with the new CID so that the old CID gets replaced. And every time that CID is updated, an event is emitted, so we have a trace of every single change. Does that make sense?
Yeah, thanks.
Thank you.
Yeah, thanks everyone. We're hitting the hour. I'm sure. We're happy to keep taking on questions. There's going to be the coffee table starting soon. It's a topic that's important for us and that we really wish to really improve on. So this is one of the areas where there's the biggest need for improvement, and we're really looking forward to being part of it. Thank you everyone for joining.
Thanks, everyone. Coffee house starts now. Feel free to stay on to discuss.